there will be also people.
Boa tarde a todos, é um prazer tê-los aqui no nosso série de seminários do C4AI. Em primeiro lugar, feliz 2024 para todos. Hoje a gente tem a honra de receber o professor Paolo Turrini, da Universidade de Warwick. O professor Turrini, ele terminou o doutorado dele na Universidade de Utrecht em 2011 e ele está na Universidade de Warwick, no Department of Computer Science, desde 2017. Ele trabalha na área de AI for Social Goods, interessado em Mechanism Design, em Multi-Agent Based Simulation, e aproveitando a estada dele de férias aqui no Brasil, ele me contatou e está dando esse seminário para a gente aqui no C4AI. Então, o título da palestra é Should We Be Loyal to Cheaters Using Reinforcement Learning to Find Out? So, thank you very much for coming, Paulo, and have a good talk.
Okay, muito obrigado. Thank you, everyone. I'm going to switch to English, if you don't mind. So, thanks a lot, Jaime, for the invite. I'm really honored to be here. I'm loving Brazil. All right, so this talk is about distributed AI, distributed artificial intelligence. And in particular, I'm studying societies of artificial agents, these small software systems, that are driven towards their own personal objectives. So they are very selfish. And I'm trying to understand a problem that is a problem before AI, is a problem of science. How can we explain how self-interested individuals, just like us, can cooperate with one another, can go beyond their self-interest, and then be altruistic, social, and so on. And I'm trying to do that using AI. So trying and teach AI to then be cooperative, even ethical, if you like. Let's see how far I got. This is very new work, so and feel free to give your feedback and feel free to interrupt me at any time with your questions. Which I'm happy to take. All right, so the overarching question is to understand pro-social behavior. We know from countless experiments, theories, but also experience that people, we are capable of altruistic behavior. We see that with like charity donations, volunteering. Every time we make a choice that takes the others into account, teamwork, collaborations in science, outside science, and so on. And the general question is, what is it that makes it possible? Because we are all very self-interested individuals, but then we are able to go beyond this. What are the conditions under which we can cooperate with one another? So let me start with a fundamental article by Martin Novak, published in Science in 2006, and a quote about cooperation in animals and humans. And Martin Novak says that cooperation means that selfish replicators, like our genes, animals, people, and so on, forgo some of their reproductive potential to help one another. So we pay a cost to make others have an advantage, right? But natural selection, the survival of the fittest, implies competition, implies my survival can be at the cost of your death. Yeah? Natural selection implies competition and therefore opposes cooperation. Cooperation is illogical unless some specific mechanism is at work. Martin Novak identifies 5 mechanisms that promote cooperation. Kin selection, giving help to our offspring because of their relation in genetic material. Direct reciprocity, I help you, you help me. Direct or indirect reciprocity, I help someone, someone will help someone else, and that someone else will help someone else, hoping that that help comes back to me eventually. Indirect reciprocity. Network reciprocity, establishing social ties with colleagues, friends, and so on, and try to create a community, a group there, group selection, the last one. So what I'm studying today is a very simple mechanism to try and understand how cooperation can come out in AI systems. But this has repercussions in, of course, also study of societies, our societies. And the game I'm going to study, the interaction I'm going to study, is a very stylized example. It's a very simple problem, but very interesting. It's called the prisoner's dilemma. For those of you who know game theory, that imagine two people that decide between an ethical and selfish behavior. Either they cycle or they drive. Imagine there is here a row player and a column player, and based on their choices, they get a payoff. So for example, if the row player decides to cycle, and so does the column player, they both get 3. This is the row payoff, the column payoff. As you might know, in a prisoner's dilemma, although both players cycling is socially good, so they get a lot of payoff, driving, so the selfish behavior, is always better no matter what the others do. So for example, if I'm the row player and you are the column player, Jaime, you cycle, then I choose between 3 and 5, so I choose 5 to drive. But if you drive, I choose between 0 and 1, I also choose to drive. So no matter what you do, driving is better for me, and so is for you. So driving is the only Nash equilibrium strategy, but if we were both cooperative, we could have gotten both a better payoff. That's a dilemma, right? The individual incentive to defect versus the social incentive to cooperate. Okay, so this is the prisoner's dilemma, and what we choose is a mechanism that we know from what Martin Novak said, that if we leave people to their individual rationality, defection is bound to emerge, because driving is always better, right? But we study here a very simple mechanism that we'll see will make cooperation arise, and it's the prisoner's dilemma with the option of opting out. So not just do I play a prisoner's dilemma with someone, but I can also choose whether to continue playing with them or not. And this is the mechanism. There are 2 steps. At step 1, I play the game with my partner, say Jaime. I choose whether to cooperate or defect. I see what they do. And then at step 2, I choose whether to continue playing with them or just be randomly rewired to someone else. Okay, so this is the mechanism. You see, it's not just the game. I also have some choice. Okay. This is called the prisoner's dilemma with the option of opting out. And you see people are matched in pairs, and they choose their behavior. All right. So this is, by the way, this first part of the talk is a paper with my postdoc, Ching-Win Leung from Warwick, that will be presented at AMAS 24 in New Zealand, which Jaime is general chair of. So yeah, he'll be there. So learning partner selection rules with the sustained cooperation in social dilemmas with the option of opting out. And this is we have this algorithm, this protocol to that is what I just told you is a bit more formal. We have a society of agents. At the start, players are randomly matched, are paired at random, and each player, second point, decides whether to continue playing with the current partner or break ties. Of course, at the first step, it's just random again. If ties are broken, both players become available. Okay. Players who did not break ties, they keep playing together. And the available players, those that decided to break up with their partner, are rematched at random. Okay. And then, okay, the game phase, each player plays a prisoner's dilemma with the current partner and receives the reward. And then we go back to step 2. On and on and on. Okay? Will agents, how will they behave? Not just in the game, but also in the partner selection. We decide to stay or not, depending on what the partners do. Okay, so 2 technical slides. We're using reinforcement learning here, in particular Q-learning, the variant of Q-learning called SARSA. And this is the thing. We have a society of agents called Agent I. Each of them is, say, Agent I, and each of them observes the partner last action. So if my partner cooperates or defects, I see that. Okay, I'm given this information, and I receive the reward associated with the current state. I will discuss briefly later what states are, okay? Just I see the action, I get the reward. So after 20 rounds, and I'll elaborate later of why 20 rounds of partner selection, gameplay, 20 times, so 40 moves per agent. Agents update their Q value, so the value of the actions, and it's updated recursively. So for agent I, the Q value of action A at state S, the new Q value, is 1 minus alpha times the old Q value plus alpha, I will explain what this alpha is, times the payoff of that action at the current state, plus the Q value of the next action taken at the next state. Remember, it's a stream of rewards. So this alpha, for those of you who know reinforcement learning, is the learning step. We optimize at 0.05 with the linear search. If you want to know more, you'll ask me questions. And since we have a Sarsa-Q learning, we have a stream of actions. So S prime, B prime is the next state. We don't have discounting factor in this formula because it's 1. Forget about it. We don't need it. It's 1. Of course, I talked about states. They are very simple states. Each agent is in 4 possible states. It's either in the game stage or in the partner selection stage. And in the game stage, I play knowing my partner has cooperated the last time or has defected the last time. At the partner selection phase, I choose to stay or switch knowing my partner has cooperated at the last stage or defected the last stage. That's all I know. Okay, 4 states. Okay, is this clear? Okay, so this is how agents update their policy. Okay, and now how do they change? How do they choose their action? This is the other technical slide. I need an exploration policy. We use the Boltzmann action selection policy, which basically means that the actions with the highest Q values have the higher probability of being selected. So this is the exponential of an action A at state S with temperature parameter T over the relative proportion with the other action's Q value, okay? And T is the temperature parameter that controls the exploration-exploitation trade-off. If T is 0, this is 1 over the number of actions, so it's pure exploration, just random. If the bigger T is, the more we go to the action with the highest payoff, highest Q value, right? So we have this trade-off, and we actually, for this simulation, we take T to be 1 again, okay? Clear? Great. Okay, so here is the most fundamental result, the most basic result of our agent society. On the right, you see a society with only random matching, no partner selection. On the left, the option of opting out, right? So let's first discuss what happens here on the left side. The purple line is the so the sum of all the agents' reward, you see, goes up, okay, over 100,000 episodes of the simulation. Remember, each episode is 20 rounds, it's partner selection game phase. The society of agents is 20 agents, so is the number of simulations we average from this. You see the variance that is shaded here. So the cooperators increase. So cooperation emerges and stabilizes later on after 100,000 rounds, is quite predominant to 80, and later on it converges to 82% of cooperator-cooperator pairs. So both agents choose to cooperate, just having this option of opting out. Okay, and the defectors, defect, you see, starts high, but then it goes down, and the other two really stay at the bottom. However, if we take the partner selection out and just say do random matching, mass defection emerges. Cooperation has no place, goes down, right? Just by introducing this action of saying, I'm happy to stay or switch without any rule, any promise on the future behavior of the opponent or the partner, is enough for cooperation under those conditions, Boltzmann action selection function with those parameters to emerge and stabilize. So if we go beyond the 200,000 rounds, this is going to converge at 82%. Okay, right. So just allowing this basic mechanism, we have this opting out. Can someone tell me how I'm doing with time? Because I'm quite bad at it normally. How long?
You have more 40 minutes?
Yeah, it's fine. Great. All right. So I'm not just interested in understanding whether cooperation can emerge, but also what kind of strategies agents employ. What are the equilibrium strategies? Those of you who know game theory, repeated games, you might have heard of tit for tat, for example, being an equilibrium strategy. I copy your last strategy, and then that is a Nash equilibrium of the repeated game, the infinite game. Here we have an extra dimension. We have a partner selection dimension. It's not just a strategy that is an equilibrium strategy in the game, say like tit for tat, but also what kind of partner selection strategies are equilibrium strategies. These two things co-evolve. It's not just what you do in the game, but also what you do outside the game that is important. Okay, and since we can observe the opponent's last action, for the game strategy, we have 4 possible strategies. So always cooperate. Whether my opponent cooperates or defects, I cooperate. That's an always cooperate strategy. An always defect strategy, whether my opponent cooperates or defects, I always defect. Or tit for tat, if my opponent has cooperated, I cooperate. If my opponent has defected, I defect. That's a tit for tat strategy. Or to close the set is the reverse one. I do the opposite. Right? There are only 4 possible strategies in the game. But then also in the partner selection phase, I'm going to have an always stay strategy. If my opponent defected or cooperated, I stick to them. It's a very loyal strategy. No matter what they do, I want to be there. I want to be with them. Always switch. No matter what they do, I break ties. But an out for that, a very important strategy, I switch if and only if my partner defects. So I stick to cooperators. I break ties with defectors. Notice that there is no promise that cooperators will remain cooperators. These two things will co-evolve. And that's the important part. Or the reverse of out for that. If you are nice to me, I break ties. If you are bad to me, I stay. Okay? That's a possibility. It's a strategy. And this out for that is very important because in the literature, there are theoretical and computational models that have found that if agents are forced to obey tit for tat, so they don't learn it, they're just forced to, then cooperation can emerge. Here we generalize this model and we say, can out for tat emerge and co-evolve together with cooperation? We don't force it. We just have agents learning by themselves. Right? Okay, and now we observe the co-evolution of strategy and structure in this game. Right? On the top, you have, you see the stay out for that, reverse out for that switch. This is the partner selection evolution. And this is the game evolution. Okay? And the episodes are the same. Like here, episode 100, out for that is already predominant. While at the game level, it's all defection. So imagine a society of all defectors with out for that rule, and stay also is there. Switch is important because, you know, there are a lot of defectors, so you can try. Now, as we go to episode 1000, out for that and stay, these two rules are already dominant, while defectors are dominating. These two evolve together. Again, as we move to episode 10,000, we now see that tit for tat is becoming a little bit more dominant, while stay and out for tat are completely dominating the other rules. So like out for tat, that will stay dominant later on, is learned much earlier than tit for tat, which you will see will dominate later on. So the defectors go down, tit for tat go up, and in the end, you have a society of out for tat and stay with tit for tat and all cooperate with out for tat and stay, which basically means a cooperative society. Because if you do out for tat with cooperators, you're cooperating, right? So co-evolution of strategy and structure, where the structural rules are learned even earlier than the game rules. You see? Great. Okay. I said if out for tat is imposed, cooperation emerges. And of course, if agents have to learn these rules by themselves, there is a cost of this. And you see that this also comes out from the simulations. On the left side, we impose out for tat from the beginning. Rewards are the purple. Cooperators come out at episode 40,000. They are already 80%. But with the old graph, they have to learn it by themselves. So they pay the cost of that. And while they converge to the same number, they do so slowly. Okay, so you need more episodes to get to this 80+% number. Great. Okay, so the conclusions of this part of the talk, and then I'll present you something related, is that, so the intermediate conclusions, let's call them, is that opting out is a minimal mechanism that is enough for a selfish-driven society to avoid the defection spreads in society. So if we didn't have any mechanism, mass defection takes over, random matching. But with this minimal mechanism, this is enough for cooperators to succeed and stabilize. Defection dominates, but agents are able, in this model, to learn these cooperation sustaining rules by themselves. And also this partner selection strategy. So not only do they learn to cooperate in the game, but they also learn to select whether to switch or not with people who cooperate or not. It's a two-dimensional timescales, what's happening here, right? So in-game and partner selection strategies co-evolve. The out for tat, it's an interesting finding, is learned before tit for tat. And this strategy of loyal state, always cooperate is very nice, but always cooperate in the game is typically invaded easily by defectors. It's the same for the partner selection rules. If you don't have a way to oust, to punish defectors, just being say I'll stay anyway, is susceptible to the invasion of defectors. You need a way to react to that, and that's what out for tat does. And there is a cost of learning out for tat. That is, if you impose the rule from the beginning, we get cooperation much faster, but agents can learn by themselves. That's the main message. Okay? And this is what we did with reinforcement learning. And this is a reinforcement learning that requires 100,000 episodes, very long simulations, 20 simulations, 20 rounds per game. It's very long. It takes a long time. So it's an offline learning protocol. In the second part of the talk, I want to talk about experiments with humans. So now we have in the first part of the talk, let's say we have constructed small AI creatures that by training a lot can learn to cooperate, can learn to be nice to one another. But what happens with humans, right? Can we have online artificial agents that simulate the way humans learn to be cooperative? So I'm not doing offline learning anymore. I'm doing online learning. Can AI systems then learn, reproduce the way people play a prisoner's dilemma game? I will start exploring this by showing you experimental results with humans and then see if we can match them using some simple learning algorithm. So in these experiments that were conducted at Warwick with our online platform Prolific, we have 6 groups of 6 people playing the prisoner's dilemma with opting out for 30 rounds. So we don't have 100,000 episodes, only 30, because we can't do experiments with people of 100,000 episodes. The only difference, because we didn't want to inform people when the game ends, we say that people who opt out need to wait until a rematching round that can happen with 1/6 probability to avoid this end game situation that is known from game theory where you defect anyway. So at the rematching round, everyone is rematched. We'll comment on that later, but it's the same game apart from this difference. Yeah? All right, so this is the group that conducted the experiments, and now we are doing the learning. They are all from Warwick, apart from Nobuki, who is from Osaka, and Charlie, now at UCL, was at Warwick before. All right, so the first interesting thing when you make humans playing this game is that there seem to be cultural differences. That is, when we did the experiment at Warwick, we observed that Warwick students learn to defect very quickly. Let's say, behaviorally, they are more selfish. But this experiment in Japan showed higher levels of cooperation, and not just even right from the start. So the Japanese subjects, they were like we're talking 200 people. They had a significant starting level of cooperation to like 80%. Warwick 60%, and you see the trend here remains cooperative with all the other actions like this: cooperate, yes, yeah, I want to cooperate and I want to stay with my partner. That is the Japan data. Warwick data, these are the rematching rounds, so there are trends in cooperation levels. the rising with people that stay to play, by the way, they learn to defect. So the peaks at the rematching round show, I don't want to elaborate too much on that, but the people that stay to play the game tend to be cooperators. So it's like the out for that rule. If you cooperate, I stay. If you defect, I go. Yeah. So, and you see these other strategies that are like cooperate yes, cooperate and stay, cooperate no, cooperate and switch, defect no, defect yes. You see at Warwick, defect yes and defect no go up, but Osaka, they don't really. Okay, so these are the data. There are cultural differences, yeah, clearly. Can we replicate these results, or at least try, using reinforcement learning only? So no social norms, no culture encoded. Can we try and see what we can do with learning? Okay, so what we do is to use very simple ancient algorithm called cross-learning. Cross-learning is a one-agent algorithm, and we do this for every agent, that has a very simple policy update, much simpler than Q-learning. That is, so each agent starts with a policy over actions. Policy is a probability distribution over actions, and they are in an environment that get a reward. Imagine they play in a stateless Markov decision process, for those of you who know reinforcement learning. So the probability distribution over actions is updated at each time step based on the reward that they get. So they roll it, the policy is the dice. I roll a dice, I get an action. So for the action I got, say I draw action A, I got reward R. Well, action A, and these rewards, very important, are always between 0 and 1, always. They are normalized, okay? The probability of action A is increased, so it's the old probability increased by R minus R times the probability to occur. Okay, and I explain why this is, because all the other actions only get the old probability minus RPX. You see, I'm adding R, and since this is a probability distribution, I'm subtracting R. I'm redistributing this reward between 0 and 1 uniformly on the other actions, but giving a bit more to the action that was taken. Okay. And this is very important algorithm because we know that it converges to the Nash equilibrium by best response dynamics from the initial policy. So we know that if agents play this cross-learning without even knowing that they're playing a game, they will end up, if they play a game, converging to the Nash equilibrium from that initial policy. A very nice result from 1997. And there is a nice survey, 2015, Evolutionary Game Theory and Reinforcement Learning, by these guys in the Journal of Artificial Intelligence Research. Okay, cross-learning. Let's try and see what happens with cross-learning. For partner selection, we split agents in group of 6 and wait till rematched. They have a policy over this stay and cooperate or defect. Yes is stay, no is switch. So they have these 4 actions policies. They start with the initial policy that corresponds to the experimental data. So we have our Japanese AI agents that start from 0.8, our English AI agents that start from 0.6. So we try and mimic this initial data and just let them run cross-learning for 30 rounds. Okay? And we look at other models. We can discuss them later if you want, but nothing to say on this. Just we can elaborate later. Okay, we also have an accuracy. This is a very maybe a tedious slide, but here I'm just saying we need a benchmark, which is and we need a measure of accuracy. Accuracy is the distance between the experimental data and the simulation data. Take the absolute distance, 1 minus that, average across all actions and all rounds. That's the accuracy. And benchmark is, suppose there was no learning from the simulation, just take the initial data. Okay. Now these are the results with cross-learning. This is a graph of cross-learning. Agents have no rules here. It just do cross-learning from the initial policy by themselves. And these are the Warwick data. Okay? So what we can notice is that the benchmark is already really high because the initial policy for most actions are really stable. And the maximum accuracy we can get is 1. We cannot get more than that. So the cross-learning has a faint improvement over the benchmark in the Warwick data. Okay? Faint improvement. Practically no improvement. Okay, but okay, shapes look good. I mean, it could have been worse, but also better. Huh? You see, some trends are replicated. On the Osaka data, they have a higher improvement, okay, on the benchmark. And you see the curves here. Agents with no rules learn by themselves, just initial policy and cross-learning. Okay, so this look okay. But then we said, okay, actually, so obviously, let me comment. There are clear similarities in the traces. And what I found very interesting is that we can, and I want to talk about that a bit more later, the cultural differences, in fact, that we have from the data is just the initial round, okay? This we can put in a reinforcement learning algorithm. It's the initial policy. It's a difference. Maybe it's not all there is, absolutely, it's not all there is about culture at all, but it's a difference that we can at least do something with, right? And we see also that learning can sort of explain some behavior, which means people don't just go in the game and decide what to do. They adapt. There is some adaptation, maybe faint in some cases, but learning is more predictive than just the initial policy. So there is some adaptation, observing what the others do. It's not just, I decide to be nice in a prisoner's dilemma game. I decide to be nice first, but then let's see what the others do, and so on. Do I stay? Do I switch? These are adaptations to my group I'm playing with. Okay. There is a spike in cooperation when people keep playing. This suggests an out for that policy. But out for that, remember, was a strategy that took the information of the other agents into account. I know the move that you did, but cross-learning does not know that. Cross-learning is just actions, rewards, action, rewards. So we don't really exploit that. Yeah. So cross-learning does not see past actions. Of course, you get the reward, and it will gonna take a long while before getting there. In the end, you'll do it, but it's very difficult to reproduce. So we decided to introduce an extension, which is called conditional cross-learning. That is, we still have the groups of 6 agents divided in cultures and so on. They observe the last action of the opponent, and we have 2 policies. The first policy is I update if my opponent cooperates. The second policy I update if my opponent defects. So before I didn't know, I just update one policy based on the reward. Now I have an explicit representation of the action of my opponent or partner, whatever. So cooperator policy updated if partner cooperates, defector policy is updated if partner defects. And again, we look at extensions with no significant improvements. And these are the results with this conditional cross-learning. These are the Warwick data. They look good. Huh? So accuracy is almost, significant now. Before it was just a faint improvement. There is more improvement. Still not perfect. Let's not forget that experiments have noise. And many actions, like this red and green, they are very stable throughout, even in the benchmark of the simulation. They are very stable. What changes is this cooperation thing. Yeah? And the accuracy is across all actions. So we were really critical with ourselves in the measure of actions because we didn't just focus on the good one, all of them. So this is the Warwick, and these are the Osaka data. Again, significant improvement here, even more than before. So yeah, and this is what we got so far, like a simple learning algorithm that all it does is to take the policy, the last action of the opponent into account, and starts with the data culture, allow me to call it like that, that is the same as the experimental data, does quite well in simulating this behavior. Does quite well. And yeah, so these are like the data I wanted to. So this is online learning. I'm adapting to what I see. I don't just simulate until equilibrium. Yeah. So this is basically I'm zooming in offline learning and looking only at 30 rounds, how the curves are. I have a lens on the offline learning. This 30 rounds, not 100,000. And I want to fine-tune the simulation so that I can replicate human behavior. That is the big goal. Of course, we can do only so much, and there is a lot more to be done. But I think I like this data. I hope you like them too. But again, a lot of validation still. This is not published yet. We just came out with these models, results now. Okay, so some further conclusions. So conditional cross-learning seems to learn, or it seems from the data, an OFT, an alpha type of strategy, so where cooperators stick to cooperators' partners and break tie with defector in the same way to match experimental data, let's say, fairly faithfully. Initial policies as a way to encode what we can encode about cultural difference, but there is a lot more to be understood, both in the offline and online learning. There is this issue of timescales. I said you can do partner selection and then game, or you can choose at every time whether to continue or not. But what happens if I can only choose after 5 times I play the game? Right? Or if I can do faster partner selection than game play. What happens if I can choose who to play with, not just out for that, but actually I know that you cooperated, even I didn't play with you. Do I choose to play with you? What if I don't even know that? I heard from someone that you cooperated a lot. You know, there's much more to be understood in these games. And I suspect that the more complex the communication mechanisms are, the more complex the learning models will have to be, because we need to take more into account. It's not just initial policy and last move. Yeah? Long-term experiments. Also, people played for 30 rounds. What happens if they played for 100 rounds? Do they learn equilibrium strategies? Do they learn mass defection, mass cooperation? That we don't know. Long-term experiments are very difficult to obtain in practice, very costly, and people get bored of clicking 1,000 times. Right? So 30 rounds are a lot of games already. Does population size matters? We had 6 groups of 6 agents, small groups. We know after a few rounds, we kind of have an idea of the population, right? And we can even influence the behavior. But what about a large population? Yeah. And here, like maybe a bit more provocative, other regarding behavior is studied a lot from the lens of social norms, ethics. The reason why I act cooperatively is not just learning, but also because I have something in my head that says, oh, this is something I should do. I should behave like this. Yeah? But it seems there is a lot of learning as well, a lot of adaptation. How far can we go with adaptation only? What are the games, the conditions when we need to add more to this in order to explain human data? And yes, with that, I conclude. Thank you very much for your attention. And yeah, thank you. Thank you.
Thank you, Paolo, for the brilliant talk.
Muito obrigado.
Good Portuguese. I was wondering if there is some questions from the audience here or in the remotes. I have some questions, but
yeah.
Mine? Okay. So for the second experiment,
yes,
you said you divided 6 groups of 6 people, right? They
yes.
were homogeneous. I mean, Japanese played only with Japanese, and Warwick played only with Warwick. You didn't do mixed stuff.
No. So the experiments I wanted to replicate were carried out with 6 groups of 6 people in Japan, and 6 groups of 6 people at Warwick. Those were carried out, and I wanted to match those experiments. So for that, we took the average policy of Japan and have agents that play that policy, and Warwick agents that play that policy. So they are homogeneous, but 2 different populations, because then, yes, that's what I did.
Okay. You didn't think in doing some mixed
I think,
experiments?
Yes. But, so there are further experimental findings that were collected at Warwick with an online platform called Prolific that considers also mixed populations. And yeah, so I'm still to see these results, to look at. They are there. I just didn't see them yet. And for those, I think we will need to mix, because every agent or every group of agents will have different behavior. So it's good to do that, and will be future work, and also to understand the role of variance, because this average policy, the initial policy was an average policy. But variance plays a role in groups. There will be more cooperative Japanese and less cooperative Japanese. They all average to 0.8, but some were less cooperative than others. So yes, mixing is good and will be done. Just haven't done it yet.
Because in real life, for instance, when you cooperate with somebody that you know it's from another culture, sometimes you behave differently and have different strategies, right?
For sure. Good point. Yeah.
A second issue is about the option of changing the partner.
Yes.
Is that a difference when both want to change, or just one?
So
because if I understood, if one wants to change, you change.
Yes. In that
So it's not the same if both wants to change.
No. If at least one wants to change, both split.
Okay.
So they cannot be together.
Individually it's different, right?
Individually
it's like, for instance, you have a marriage.
Yes.
If both wants to separate it,
That's
one
fine.
thing,
That's
what
fine.
one wants to separate and the other not, it's different.
But in this marriage, divorce is allowed from one person only. That's enough. Okay. And these are the experiments as well. But I agree that you will see there is so much data we didn't look at. I'm sure that the behavior of people where they both wanted to change will display some features. I'm pretty sure that will be special. So we need to look at that. Yeah. But the rules of the game, as in the experiments and simulations, are such: if one of them wants to break ties, ties are broken. That is it.
Yeah. Some other question from the audience? No? Remote? So I just want to add that in your introduction, when you mentioned the science, it's a Science or Nature paper. Science. It was from 2006.
Yes.
And there is the work of Cristiano Castelfranchi in the 90s. Yes. I worked with him. So the story of how cooperation evolves or arises that is prior to this
for sure.
reference, because there are people that have studied
100%. Before. I know that paper. Yeah. Yes. This is like, it's not like the work of Martin Novak is not just about saying there are these rules, but also establishing the mathematical conditions on the proportion between in the game, again, prisoner's dilemma, the rewards, the benefits, and so on, and linking it to all this like a general theory. But I'm aware there is a lot of other work as well.
I would like to congratulate you for the seminar and for the research. I think it's very interesting. Yes. We have Joca here, which is from the humanities, and normally in our AI center, let us say, putting together people who, from a technical view of AI and a humanity think of AI, sometimes is difficult. For instance, there is something that you mentioned here that can be something to think about, is that in a certain way, not complete, not the whole truth, you can try initially to model culture as an initial condition of an equation. Of course, culture is bigger than that, but there is some kind of methodological using math that allows you to do that, even if it's not complete or have a lot of other directions to do. It's simple, but it's a way of doing it, and we have some insights then too. I was just commenting with him when you showed that the number of defectors are different. In the beginning, you said in Warwick it was, and I was talking to him that if you do a Brazilian, probably it will be more selfish.
That's not my experience. That's not my experience.
But I'm telling you that probably there will be that. Okay. Thank you very much for coming. You are welcome to be. Thank you for you who are online, and you can see it the talk afterwards if you want to be able to do it online. Thank you, and to the next seminar. Bye-bye.